Hello everyone, this is Professor Roman. Let's continue the group theory lectures. Now let's discuss a few simple examples of normality, and we'll consider some additional examples a bit later. First, let's observe that if G is a group generated by the generators A1 through AN, and if H is a subgroup of G generated by the elements B1 through Bm, then H is normal in G if and only if each of the generators of H, when conjugated by a generator of G, remains in H. And this follows from the very nice properties of conjugation, and I'm going to leave it for you to prove. Example, every subgroup of an abelian group is normal. If G is any group, then the trivial subgroup and the non-proper subgroup G itself are normal in G. The center of any group is a normal subgroup in the group, as is any subgroup that is contained in the center. It will be normal in the group. Now you may recall that the kernel of a homomorphism, sigma from G to H, is the subgroup consisting of all elements of the domain G that are sent to the identity element in the codomain H. So this is what it looks like in symbols. The kernel of any group homomorphism is a normal subgroup. And here's the reason. If we take an element A in the kernel and an arbitrary element G in the group, this is the domain G, then we need to show that GAG inverse is in the kernel of sigma. So when we apply sigma to GAG inverse, it looks like this. We can pull the inverse outside here, so this becomes sigma G inverse, but sigma A is 1 because A is in the kernel of sigma, so this collapses to 1. Later on, we're going to show that any normal subgroup, N of G, is the kernel of a homomorphism. That homomorphism is called a natural map. So actually the concepts of being normal and being a kernel are equivalent. And that's another reason to study normality, because it characterizes those subgroups that are kernels of some homomorphism. Theorem 8.3 told us that gigantic subgroups are normal. So for example, since the alternating group is gigantic in the symmetric group, the alternating group is normal. It's a normal subgroup of the symmetric group. Also, the subgroup generated by rotation in any dihedral group is gigantic. It's half the size of the dihedral group itself, and so it is normal. You could call that the rotation subgroup. It's normal in the dihedral group. Let's take a look specifically at the dihedral group D8, generated by reflection and 90-degree clockwise rotation. These are the symmetries of the square. The subgroup generated by rho squared is normal in the dihedral group, and to see that, we need only check by our original comment in this lecture, in this section, that the generator when conjugated by, this is the generator of the subgroup, when conjugated by either generator of the full group, remains in the subgroup. So rho squared conjugate by sigma. There's a little clash of notation here. These two subscripts have entirely different meanings. And it's a little unfortunate, but usually from the context you can sort that out. 2 does not belong to the group, so you can't conjugate by 2. This has to be rho squared. And sigma is not an integer, so you can't use it as an exponent in the for multiplication. So it's got to be conjugation. Anyway, so this is what the conjugate of rho squared looks like, because sigma is an involution, and this, from the commutativity properties of the dihedral group, is rho to the negative 2, which belongs to the subgroup. And if we conjugate rho squared by the other generator, rho, we get rho squared, rho inverse, and that's just rho squared, which obviously belongs to this subgroup. Okay. So the subgroup generated by rho squared is normal in D8. Okay. As to the quotient group, D8 mod the subgroup generated by rho squared, its order is the order of D8 divided by the order of this group. Rho has order 4, it's 90-degree rotation, and so this quotient group has order 4. So we need to identify 4 distinct cosets for this subgroup, and we will have the quotient group. The elements of D8 look like this, and so these are all the possible coset representatives. Every element is a coset representative for a coset it belongs to. And so this is a complete list of the cosets, but with lots of duplications. But rho squared obviously belongs to the subgroup generated by rho squared, so it can be absorbed into the subgroup. So when we have something that looks like rho squared times the subgroup generated by rho squared, this is nothing more than the subgroup generated by rho squared. So this one can be left out because it's in fact the same as that one. And we can continue to trim here the rho squared, and this rho cube, we can split that into rho times rho squared. Rho squared gets absorbed. So it's the first 4 cosets that are distinct and give a complete set of cosets. So this is the quotient group. Now, since sigma squared is the identity, sigma is an involution, and since sigma rho squared simplifies to the identity as well, and since rho squared belongs to the subgroup generated by rho squared, every one of these non-identities, so the 3 non-identity cosets here, has order 2. Well, this means that it's not the cyclic group of order 4. The only other group of order 4 is the Klein 4 group. So this quotient is actually isomorphic to the Klein 4 group. So it is a Klein 4 group. I don't know if we've discussed this, but you have the machinery now to determine all subgroups of order 4. And so that's probably something you should think about for good practice. Another example, this is the set of all 2 by 2 matrices with integer entries. It is a group under addition. This is the subset of G consisting of all 2 by 2 matrices whose entries are even integers. And E is in fact a normal subgroup of G, and the quotient group looks like this, and I will leave that for you to sort out. Since normality is such an important concept, it is worth characterizing it in as many ways as we can find, because we never know which way is going to be useful at a given moment. So here is a theorem. The following are equivalent. H is a subgroup of G. H is normal in G. Every right coset of H is a left coset. So that is to say that if A is in G, then there is a B in G such that HA equals BH. Every right coset is a left coset. It does not say they have to have the same coset representative. Every left coset is a right coset, and this one's very nice, can be quite useful. If A and B are in G, then AB is in H if and only if BA is in H. I would suggest to you that you stop the video if you're watching the video, or stop reading the book and try to prove this yourself. That's generally a good thing to do in all cases for proofs. But these proofs are not terribly difficult and would give you some good practice. Okay. If 1 holds, if H is normal in G, then we know that AH equals HA, and so 2 holds almost trivially. On the other hand, if 2 holds, then for a given element A and G, because HA equals BH for some B, that B has to be a little h times A for some little h in the subgroup, and so HA is BH, which is little h A capital H. Now we move the little h to the other side, becomes little h inverse, but it gets absorbed in the subgroup. And so we have HA equals AH, and that is one of the normality conditions. Okay. One equivalent way of expressing normality. So H is normal in G. So what we've shown is that 1 and 2 are equivalent. And I'm going to leave it to you to deal with number 3 here. For part 4, if H is normal in G and AB is in H, then A is in HB inverse, which is equal to B inverse H, because H is normal, and therefore BA belongs to H. We move the B inverse to the other side. And by symmetry, we can interchange the roles of A and B. We will have BA in H implies AB is in H. So the normality of H does imply that this property holds, is biconditional. And conversely, if this holds, we need to show H is normal, then take a little h in H and any element A in G. HA inverse A is, of course, just little h, which belongs to capital H. Now we can use this property. It tells us we can reverse the order of the factors, and doesn't mean it's the same element, but it still belongs to the subgroup. So when I interchange these factors, it looks like that, belongs to the subgroup. That simply says that little h, no matter what you conjugate it by, remains in the subgroup. So h is normal. We can think of normality, and in particular this way of expressing it, AH equals HA, as a kind of rather vague commutativity rule. And by that I mean that if little a is an element of the group and little h is an element of the normal subgroup, and we take the product AH and want to swap the order of the factors, we can do so, but A crosses without change, but H may turn into a different element, but it has to belong to the normal subgroup. Okay. And same thing going in the other direction. If you have HA, that will be AH prime for some H prime in the subgroup. So we can reverse the order in a product AH or HA. We can send A across H in either direction. The price we pay is that the element H in the normal subgroup may change to a different element, but it still must be in the normal subgroup. And that turns out to be rather useful. We're going to use it a few times ourselves at key moments. It does take a bit of practice to get used to quotient groups and to manipulate cosets. So don't be discouraged right away if this concept seems a little vague to you. Some practice will clear that up. Aside from the coset product rule, which is pretty straightforward, it's useful to keep this fact about equality of cosets somewhere in the front of your mind. AH is equal to BH if and only if B is equal to A little h. So it's an H. B is an H multiple of A. Okay. Also, the size formula is often useful in some contexts. But the main reason that dealing with quotient groups takes a bit of care and a bit of practice is because each coset has many coset representations. Coset representatives, I'm sorry. This should be representative. Okay. And that follows from this expression here. In words, basically, every element of a coset can be used as a coset representative. What this means is we often have an issue of well-definedness. It's always tempting to make a definition using a coset representative, but you have to be sure that your definition does not depend on the choice of coset representative. So to be a little more specific, suppose we want to define, say, a function sigma from G mod H to some other group K. And we write something like this: sigma of AH equals, and this is meant to be some expression in A that belongs to the codomain K. Okay? A squared or whatever, it doesn't matter. Some expression involving A. Well, we have to immediately check that that sigma is well defined. So we've got to ensure that if we have two different representatives for the same coset, that they call them A and B, that f of A is equal to f of B. Otherwise we have an ambiguity, and basically we have garbage. So just as a simple example, suppose that E is the subgroup of the integers consisting of the even integers. And we define a map sigma from Z mod E to Z, and now we have an additive group here, so cosets are written A plus E. Sigma of A plus E is A squared. Well, here we've got a problem. This is not well defined. It may look just fine. And if you're not really conscious of this problem of different coset representatives and well-definedness, you might just skip over. You might say, okay, great, I have a function. But in fact, for example, 3 plus E is the same coset as 5 plus E because 5 minus 3 is even. But 3 squared, and this would be f of 3 as we had here, 3 squared and 5 squared are certainly different. So what we have here is not well defined. It's useless. I wanted to include a couple of things that would give you some more practice with cosets right away. And so I included this theorem, and I encourage you to try to prove it yourself. In fact, I'm not even going to read through this proof with you. If G is the essentially disjoint, that's this big dot here, set product of subgroups H and K, and if K is normal in G, then it's also normal in HK. HK is a subgroup because K is normal. So this factor group, HK mod K, is actually isomorphic to H. And you can't factor by H unless it's normal. So you've got to ensure one of these is normal so you can do this factoring. And the way you would prove this is to define a map. Now you can go in either direction. You can define a map from HK mod K to H. Then you want to show, you're trying to define an isomorphism, so you define the map, you show it's an isomorphism. Or you could define a map from H to the quotient group and show that that's an isomorphism. I did this in only one direction, but you should do it in both directions. You should try to find both those functions because there's a little bit of a moral there. If you can do the two proofs that I just outlined, you should think about which proof is, say, a little less stressful, and there's a reason for that. So I'm going to let you think on that. Another interesting example, a fact about quotient groups that we will look at in a later chapter is something that's called the third isomorphism theorem. We're going to discuss all 3 isomorphism theorems later in the book, but I wanted to present this one so you have a chance to see if you practice your skills with quotient groups. First, a definition. A tower, H subgroup of K, subgroup of G, we've talked about this before, in which both of the subgroups H and K are normal in the parent group G, is called a normal tower. And you have to be careful here. It's not sufficient that H be normal in K and K be normal in G. Transitivity of normality does not hold. That would not mean that H is normal in G. But if we know H is normal in G, H will also be normal in K. It only works in one direction. So normal tower refers to the stronger of the two statements, that K is normal in G, but H is also normal in G, not just in K. So the third isomorphism theorem says the following. Let G be a group and let HKG be a normal tower. Then K mod H is normal in G mod H. Okay. So we're factoring by H. We factor K by H and we factor G by H. K mod H is contained in G mod H, so this should be, can't really confuse this. But the statement is that K mod H is normal in G mod H. And G mod H mod K mod H is isomorphic to G mod K. This, too, you can prove. Well, you can prove the normality just using the definition of normality. And for the second part, you want to define a map and show that it's an isomorphism. So I'm going to leave that for you. We're going to do it later in the course. Now, these two theorems that I just outlined for you make it tempting to think that quotient groups behave a lot like quotients of real numbers, and in some ways they do. Little h, little k, these are real numbers now. Hk over h is equal to k, and a over h divided by k over h is equal to a over k, and those mimic the two theorems we just discussed. But one has to be very careful here. First of all, this observation does provide, perhaps, for you a useful mnemonic device. In other words, it might help you remember the two theorems. But there are two caveats here. First, there are several conditions that must obtain before the isomorphisms in those two theorems hold. So we have to have normality conditions, essential disjointness in one case, and certain containments. So the situation's a lot more complicated for groups than it is for real numbers, as far as arithmetic is concerned. Okay. And the second thing to keep in mind is that it would be very unwise to extrapolate these two cases and conclude that quotient groups behave like quotients of real numbers in other ways as well. They may, but they certainly may not. So you have to be careful not to jump to any conclusions. One of the most useful properties of normality is given in the following theorem. Let G be a group. The intersection of any family of normal subgroups of G is normal in G. So put another way, this family, NOR of G, NOR of G, and I hope I introduced this earlier, I can't remember, but this is just a notation for the family of all normal subgroups of G. Just as we had sub G for all the family of all subgroups of G, NOR G is the family of all normal subgroups of G. This is an intersection structure as well. Sub G was an intersection structure, so is NOR G. Now, because sub G is an intersection structure doesn't imply that NOR G is. It only implies that the intersection of any family of normal subgroups is a subgroup. But what we're saying here in this theorem is that the intersection is in fact also normal, so remains in the family. That means NOR G, like sub G, is a complete lattice. And the proof is quite easy. If we have a collection of normal subgroups of G, we want to show its intersection is normal, so we conjugate the intersection by any element of G. And because conjugation is so nice, remember the conjugation function is an automorphism, it will slip inside the intersection sign, and we'll have the intersection of ni conjugate by A, but the ni's are normal, so it's just the intersection of the ni's. So the intersection of this family is in fact normal. Now it's worth mentioning, I think I already did, but I guess I should have, it was a little premature. Let me emphasize then a property that is not held by normal subgroups. Sometimes it's important to know, in fact, oftentimes, what doesn't work as well as what does work. Okay. The subgroup property is transitive. If H is a subgroup of K and K is a subgroup of G, then H is a subgroup of G. The property of normality is not transitive. It is possible to have H a normal subgroup of K and K a normal subgroup of G, and yet H is not normal in G. After all, this first normality says that H is closed under conjugation by the elements of K, not the elements of G, the elements of K. And just because the K is closed under conjugation by all elements of the group does not mean that H is. Okay? So I left it as an exercise to find an example to demonstrate this. A couple of quick remarks about normal subgroups and set products and joins and things. Normality does play a role in determining when a set product, HK of subgroups, is a group. It is a subgroup. We've already seen that HK is a subgroup if and only if H and K permute HK equals KH. And let me just emphasize here, I probably should have done it when we first discussed this, or maybe I did, but the subgroups permute here, or they commute under set product. That doesn't mean they do it on the element level. Little h, little k is not necessarily equal to little k, little h. Okay? Now, if one of the subgroups, H or K, is normal, say, for example, it's K, then H and K will permute. And so HK is a subgroup of G. Moreover, if both factors H and K are normal, then the set product is normal. And I'm leaving this for you to verify, these statements concerning the first part. So, and I went ahead and I took care of it for you for the second fact. If you conjugate HK by an element A, you can split that this way, and since each of H and K is normal, this just says HK. So we have a theorem, let G be a group, and let H and K be subgroups of G. If at least one of H or K is normal in G, then H and K permute, and so HK is a subgroup of G. If both H and K are normal, then the set product HK is also normal. But the converse does not hold. If HK is normal in G, that does not necessarily imply that either H or K has to be normal in G. And that I left as an exercise. We had a theorem back in Chapter 5 that told us that the join of a permuting family of subgroups of a group consists of the set of all products of elements where the factors come from different members of the family. And since normal subgroups permute, this applies to any family of normal subgroups. In general, just to be clear on this, the join of a family of subgroups is the set of words over the members of the union of that family. And you have to take positive and negative exponents, so you have to take inverses also. But those products may have factors, separate factors that come from the same member of the family. But if you can, if the family is permuting, pairwise permuting, you can gather together the factors that come from a single member of the family, H sub I. Now, this gathering process may change the members, may change the factors, but they remain in the subgroups as the same subgroup as the original factors. So that accounts for this statement here. And this is definitely something we're thinking about. I debated whether to write all this out in more detail. It already is nasty. We've got double subscripts here. And I decided it would be better for you to see if you can do it. I don't want this to sound negative, but you may have to agonize over this briefly to get the full picture here of what I'm saying. Okay, and that's good exercise. Let me remind you, we did discuss very briefly the notion of simple groups when we talked about the classification problem for finite simple groups. If G is a group, then the trivial subgroup and the entire group are always normal. But a group is called a simple group if those are the only normal subgroups, just the trivial group and the whole group. There's the definition. The study of simple groups is really key to an understanding of the structure of all groups. But it's, in general, very difficult to determine whether or not a group is simple. And we'll have more to say about that. In fact, what we're going to do in a later chapter, where we look more closely at the symmetric groups, is show that the alternating group, AN, is simple as long as n is different from 4. A4 is not simple, but all the other alternating groups are simple groups. What is the opposite extreme of a simple group? A simple group has only two normal subgroups. The two subgroups it must have normal, the trivial group and the trivial subgroup and the whole group. The extreme opposite of that would be a group in which every subgroup is normal. Groups with that property are called Dedekind groups, named after Richard Dedekind, who is a brilliant mathematician. We've talked about him. Richard Dedekind, he contributed quite a bit to group theory, also to the foundations of mathematics and to lattice theory. Now, all abelian groups are Dedekind groups, but that's not particularly interesting, or it's not particularly enlightening. If everything commutes, everything's normal. Dedekind himself referred to non-abelian groups in which every subgroup is normal as Hamiltonian groups. This is named after the Irish mathematician William Rowan Hamilton. And we're not going to study Hamiltonian groups in this book because they really are beyond our scope of even a comprehensive introduction to group theory. But I did want to mention two facts without proof. Well, the first one is that the quaternion group is Hamiltonian, and that's something you should be able to prove. I think one of the earlier exercises was for you to find all subgroups of the quaternion group, and you can check to see that they're all normal. The other fact is that there is a characterization of Hamiltonian groups. It's quite interesting. The proof is quite difficult, and it's in my advanced group theory book, and I spent a little time seeing if I could figure out some way to simplify the proof so that I could include it in this course. But so far I have not been successful. The proof involves some concepts we haven't discussed, commutators and commutator subgroups. So I don't think I'm going to be able to figure out a way to reasonably cover the material, the proof, in this course. If I do, I will do a later lecture on it. Here's the theorem. A group G is Hamiltonian if and only if G is isomorphic to a direct product, Q8 direct product A, direct product B. Q8 is the quaternion matrix group, or in fact any quaternion group because they're all isomorphic. A is an abelian group, all of whose non-identity elements have order 2. They're all involutions. Square anything in the group, you get the identity. And B is an abelian group, all of whose elements have odd order. So this is a curious result. One thing it does say in very loose, informal terms is that in some sense the non-abelian portion of any Hamiltonian group is quaternion. So that must say something rather special about the quaternion group. Let's consider now some additional examples of normal subgroups. In example 621, we discussed the quaternion template, and we showed that this template is satisfied by an essentially unique group. Moreover, since the quaternion matrix group, which I'm denoting by Q8, this was first introduced in Chapter 2, does fit the template, we can use that group to explore the group theoretic properties of any group that fits the template, that is to say, of any quaternion group. Since they're all isomorphic, they have the same group theoretic properties. And it's much easier to work with little 2x2 matrices, because we understand the algebra quite well. I believe that it was an exercise or possibly part of an example that invited you to show that the non-trivial proper subgroups of the quaternion group are these 4 subgroups. And I'm going to leave it to you to show that they're normal. And so the group, any quaternion group is Hamiltonian. The special linear group SLN of R, these are the n by n real matrices that have determinant equal to 1, is normal in the general linear group. Because if we conjugate a matrix A from the special linear group by any matrix in the general linear group, and take its determinant, the properties of determinant's multiplicative, give us this. Determinant of A is 1. Determinant of x inverse is the inverse of determinant x, so this all collapses to 1. And so the conjugate of A also belongs to the special linear group. Here's a slightly more complicated example. Let R be the additive group of real numbers. It is abelian under addition, and the set of integers is a normal subgroup of R. It's a subgroup, and all subgroups are normal because R is abelian. I want to look at the quotient group because it's kind of interesting actually. R mod Z. Two cosets, R plus C and S plus C, are equal if and only if the difference S minus R is an integer. And so R mod Z is in fact the set of all cosets where the coset representative is in the half open interval 0 to 1, closed at 0, open at 1. And this reduction here of the coset representatives will give us distinct cosets. So this is the set of distinct cosets in the quotient group. To define addition, we add the coset representatives, but this may fall outside this interval, so we'll reduce it. Take an integer, any integer can be translated into this interval by adding or subtracting an appropriate integer. So that's what the bar refers to. Translate the expression under the bar until it's by integers values until it's in the range 0 to 1. Now, this is not the most pleasant description of the quotient group R mod Z. It's okay, but it would be nice if we could find something perhaps a little better, maybe a more familiar group that's isomorphic to R mod Z. Well, as you may know, every complex number on the unit circle, this is the complex unit circle in the complex plane, can be written in the form Z equals e to the 2 pi Ri, where R falls in this same half-open interval that we've been discussing. So the unit circle in the complex plane is the set of all of these complex numbers. And we denote it by S1. This is a relatively common notation for the unit circle in the complex plane. This is a subgroup of the multiplicative group C star of non-zero complex numbers. This is a group under multiplication. Also, the map sigma that sends the complex unit circle to this quotient group, sending e to the 2 pi Ri to R plus C, is a group homomorphism. And I'll let you check. Oh, I guess I did it for you. But what's interesting about this is that S1, the domain, is a multiplicative group, whereas the codomain is an additive group. Nothing wrong with that. Remember that a multiplicative group is simply a group where we use the multiplication for the binary operation. Here we use addition for the binary operation. There's still binary operations, still group products. Well, I guess you would call this a group sum, maybe. So there's no reason why you can't have a homomorphism from a multiplicative group to an additive group. This is the reason it's a group homomorphism. I'll let you read that for yourself. Also, sigma is injective. And to see that, we look at the kernel. If a complex number on the unit circle is taken by sigma to the identity coset, so that is 0 plus z, or just z, then by definition of sigma, this is r plus z equals z, and so r belongs to z, but also to this half-open interval, and the intersection here is just the set containing 0. In other words, r is 0. And so the only element, the only complex number in the kernel of sigma is e to the 0, because r is 0. E to the 0 is 1. Now this, not to be confusing here, this 1 is a complex number. 1, it lies on the unit circle and the positive real axis. So its coordinates in terms of order pairs are 1, 0. Also, sigma is surjective. That's pretty easy to see from the definition, and so it is an isomorphism between S1 and R mod Z. So the additive group R mod Z, which arguably is a little unpleasant, is actually isomorphic to the multiplicative group of complex numbers on the unit circle. So that's kind of nice. The special orthogonal group, SO2, I don't think we've discussed that. This is the subgroup of the orthogonal group that consists of just the rotations. Okay, so no reflections. The rotations, of course, about the origin. And this group there is also called the rotation group. And the rotation group and the complex unit circle are isomorphic as groups, and I'll leave that for you, but you can kind of see a point on the unit circle defines an angle and therefore defines a rotation. And so R mod Z is isomorphic to the rotation group. And this is a group under composition, right? So that's kind of interesting too. We have this little weird additive group, R mod Z, and it's isomorphic not only to the unit circle in the complex plane, but to the rotation group. Another example, let G be the subgroup of the general linear group that consists of matrices that look like this. They have a 0 in the lower left entry, and the A times D is non-zero, so this is a non-singular group matrix. And let N be the subset of G that consists of these matrices. Then N is normal in G, and all you have to do is conjugate an element of N by an element of G and do the matrix algebra, and you will find that it is in N. We have discussed at some length the Euclidean group E2 of isometries of the plane and its two nice subgroups, the translation group and the orthogonal group. And we learned that E2 is the essentially disjoint set product of T2 and O2. Now, if tau sub A is translation by A, and sigma is any member of the orthogonal group, then because the members of O2 are linear maps, they can be represented by matrix multiplication, if we conjugated this translation by a member of the orthogonal group, this is first of all, we translate sigma inverse of x by A, so we add A to sigma inverse of x, then we apply sigma, and that gives us x plus sigma A, so that's translation by sigma A. So the point here is that if we take a translation and we conjugate it by a member of the orthogonal group, it gives us another translation. But since the translation group is abelian, we know that if we take our translation tau sub a and we conjugate it by any translation, we get another, we get, in fact, the same translation. And since every element of E2 is a product of a translation and a member of the orthogonal group, it follows that for any sigma in E2, when we conjugate a translation by sigma, we get another translation. So the upshot is the translation subgroup is normal in E2. We proved that in 2 steps, and this is something worth thinking about because sometimes we have to do that. We didn't just take a member of the Euclidean group and try to conjugate a translation by it. We recognize first that a member of the Euclidean group is a product of a translation by a member of the orthogonal group, so we did 2 different conjugations and pieced them together. Could have done it differently, but I wanted to do it this way just for style, I guess. I'm going to leave it to you to show that the orthogonal subgroup, however, is not normal in E2.